All right, good morning. Just waiting for you guys to join. A moment. All right, I still don't see anyone in the waiting room. I'll just pause the recording. It's 11:16. I haven't seen anyone. All right, good morning. Morning,
sir.
All right. So you remember, I think it was last week or so, I told you guys that the way I want to teach the class is based off past papers, right? I actually have the first past paper ready. Let me just screen share. So we're gonna do the.
I was trying to turn in. I wanted to do the homework, right? Like the keys on my keyboard on my laptop are like not working. Like when I press N, it gives me MN, and when I press the letters, like they give me different letters, and when I press the space bar, it does random things, and the enter signs. I'm struggling over here.
Yeah. Okay. So you can use that on-screen keyboard. You know what it is? I think every laptop has one. On-screen keyboard. Just type that in, and you can basically type with your mouse instead of using a keyboard. So you just select the different letters you want to press. Yeah. So if some keys are not working on your keyboard, just press the key that you wanted to use.
Thank you, sir.
You're welcome.
I didn't know I was supposed to do work today.
You're welcome. So I said that we're gonna do the first past paper today, and I'm just gonna share. We're gonna do the 2019 paper 2, question 2. I know, I know you guys are like scared already, but it's not hard. It's not hard.
Is it a drawing?
So you're gonna do sketching to answer paper 2. So remember that for every paper 2 question, you're always gonna sketch something. Only question 1 on the paper 2 you draw on AutoCAD. Remember that. So on paper 2,
ask you to like sketching like orthographic and stuff.
Yeah, so they're gonna ask, for example, sketch. Yeah, I realize that's what we need to improve on. So let me write the paper 2, question 2 are generally sketches. And paper 2, question 1 are AutoCAD based questions. All right. So question 2, it says, make neat proportional orthographic sketches to illustrate the specified engineering conventions in the following. All right, let's break it down.
The words that confuse me.
I know, that's why I said let's break it down. So when it says proportional, let's break down terminologies, vocabulary. Let's break it down. Proportional. What comes to mind when you think of proportional?
Something
dividing or division.
Okay, so let's go for a quick definition. Proportional. So when you think of a proportional drawing, right, it's corresponding to size. So for example, here's the definition. Corresponding in size, or it's amounting to something. So if, for example, you're drawing to a scale, then every aspect of that drawing is proportionate to that scale. Understand? But in regards to sketching, what it's essentially stating is that, let me just draw right here. If you're drawing a line here, at no point in time should the opposite extent be longer than this. This would not be a proportionate drawing. Understand?
Yeah.
Right. So at no point in time should this length of the line be longer than that. It's not proportionate if you have a length or a side that's longer than the other one. So it must be corresponding to size. That's what proportionate really means. Right? So in regards to this orthographic drawing, it's essentially stating that make sure that your sketches look proportionate where both sides correspond to the next. Understand? And we're going to break it down even further. Engineering conventions. Right? When you say conventions, it's basically something that everybody agrees on. Let's say, for example, our class. It's a convention that you join 11:15, right? Something that we all agree on. Understand?
Yeah.
So if we're talking about different engineering conventions, it must be different principles that, for example, America agrees on, Britain agrees on, different countries agree on. That's why we say engineering conventions. It's something that everybody comes together and say, you know what? That means orthographic. This symbol means first angle projection. That's what it means. So let me put that, conventions. Something that is agreed upon. Everybody with me? So the question says that we're not supposed to spend more than 30 minutes on this section. And this is why I said no, that when we're doing exams, we need more time, because section 1 would have given you 2 hours to do the question, right? And then section 2 is 30 minutes. So 2.5 hours is typically the length of the exam. But let's just go through here. So now the first orthographic that they wanted to draw is something called diamond knurling. And we're going to go through that. So let's go to diamond knurling. Everybody seeing here? Diamond knurling.
Yeah.
So knurling is simply a process. Break it down further. A process is something that you do. So when you're engineering, for example, a machine part, let's say this lamp. If I'm engineering this lamp, I can do something called diamond knurling. And I basically, when I do something called diamond knurling, it gives me a grip, a better grip on that part. So let me give you a diagram to explain. Look at this for me. When I put a pattern, for example, on a, let's see, on a lever, right? Like when you're spinning a lever, don't you see that little designs on the lever that make you grip it more?
Oh, the swirling.
Right. So that's what you called knurling. Let's highlight that. So whenever you see little,
text Josh and tell him to come to.
So whenever you see little designs on, like, for example, machines that enable you to grip it more, you call those process diamond knurling or knurling on a whole, because you have different types of knurlings. But the one that we're looking on is called diamond. The reason why it's called diamond is because you have lines intersecting. When you have multiple lines intersecting, you have a diamond pattern. Everybody understand?
Sir, are these things like in a book, like this book or anything?
It's in your textbook, but I'm pretty sure no one has a textbook, right? But I gave you, hey, what's up? So these things are in the textbook. It's on the portal, right? Let's go under resources and you're gonna see 2 textbooks called engineering graphics and then engineering. So yeah, so I'm just really screen grabbing and breaking apart the questions using the textbook. So Josh, we're just talking about, for example, we're doing paper 2, 2019, right? And we're doing question 2. So we just started and we just explain what diamond knurling is. So Josh, have you ever really used a lever and you see some patterns on it that helps you to grip it more? Like when you're pulling a device and it has like some little design on it that helps you to grip it. Let me see. For example, trying to think of a good example, but right, like when you're opening a window, right, and you see those little etchings on it that makes you grip it and pull it down. Those were made from diamond knurling or knurling on a hole, which is essentially you using a machine and embedding lines on it, either straight lines or diamond. And when you put diamond, you essentially have lines at an angle that intersect. And many of those now, yeah?
So it's basically for grip, like the handle of the bike.
Right, exactly, right? And let's look at now, how can you represent this as a convention? What we said about convention is simply something that everybody agrees on. So how could you tell me, for example, when you're drawing a bicycle, that part is having grips on it? When you're drawing a lever, that part has a grip on it. We use something called an engineering convention to explain in different scenarios what we're doing. Let's look at how we draw an orthographic projection for a diamond knurling. So you would sketch essentially this for me. Let's break it apart. What does this look like? Just like a beam, right? Like a piece of metal, right? Yeah. So essentially, whenever you're sketching these types of parts, you sketch it on a piece of metal, just to literally explain what it would look like, right? So you would sketch this piece of metal right here, this box, then you would draw the pattern on it. This part now essentially tells me that, hey, this has a hole inside of it. So you know that it's a machine part. So you could literally use a pencil and on a paper, just practice sketching these devices because they're going to come on your exams, right? Let's go over the steps again. So this is what you use when you're having diamond knurlings, lines intersecting, and this is going to be the pattern for straight knurling, right? Lines are just horizontal. So this is how you would answer the question, right? By drawing this square right here, creating the pattern, and then insert a beam design right in front of it, such as this. Right? You can practice these after. You'll have the notebook to just practice them after, and time yourself to 30 minutes. You shouldn't spend more than 30 minutes on doing these questions. So everybody understand this part of the question?
Yes, sir.
Good. So we're going to go to the next part. So that was question 1. It said now, use an orthographic view to explain external threading. We just did diamond knurling. We're going to do external threading. Let's go step by step. Okay. When something is external, what does it mean?
On the outside.
Right, exactly. So if I have, for example, a piece of metal, right? I'm doing something on the outside, correct? Right. Have you ever seen a screw? Right? You know, screws you put in like in different machine holes and stuff. Those
Yes,
those swirls that you see around the screw are called threads.
Yes, sir.
Right. So let's look at it.
And bolts too.
Yeah. So no, but the ones on the bolts now are gonna be internal. Because remember, external means that it was on the outside, but when you have bolts now, it's gonna be on the inside. I mean nuts. When you have nuts now, it's gonna be on the inside. So there are 2 types of threads. External ones such as screws, right? And then internal ones such as nuts. And the definition of a thread is simply a cut on the shape itself. That can be on the inside or the outside. So that's really just threads, just designs on screws and different patterns like that. Right? Let's look at how you would, let me give you an example quickly. So an example, how you would look on a rough path is really like this. You still have the same beam like I said a while ago, and you would just detail for me that there's jagged lines. Easy as that, right? Then for the internal one, remember, if I'm having, for example, a nut, let's go back to the nut picture. Right? You couldn't tell me that the threads are like this, because this would essentially be on the outside. You would need to somehow tell me that the threads are on the inside, right?
So, sir, I couldn't draw like a nut myself and then kind of just put, you see how the diagram is there?
Yeah.
The nuts horizontal in a way, but kind of parallel.
Exactly. Yeah, so that's what you do. So you would draw the nuts like you stand it up, and you would draw exactly what you would see on the inside. So when you cut that nut and you're trying to look at what exactly the pattern is, you would just see some horizontal line going across, right?
Yes, sir.
Right, so this is how it would look on a simplified scale. But let me give you a better diagram to explain. So here's the orthographic sketch. Right? So for the external thread, because remember, the question didn't ask us for internal, so you don't have to worry about that. For the external thread though, all you would do, guys, is just draw a beam like you did previously and just create a 45 angled line right above. So here's where the beam stopped. This line below it right here. You see that? To create that you're drawing an external thread like the pattern on the groove, you would draw a 45-degree line going up, then you just continue a parallel line above it. Does that make sense?
Yes, sir.
Right, good. Remember, you have the video to watch over and everything. And to represent it as an plan view, when you're looking at it directly downwards, you would essentially just see a circle, because a screw at the end of the day is really just a elongated cylinder. So you would just see a circle, right? And then you would tell me that there's 2 parts of that circle, the internal part and the external part, which is the grooves. And that's it. So these questions, students always stumble over. That's why I'm spending the most time on these questions. Because you see, the question 1, everybody can handle it. It just asks you, for example, draw this orthographic in isometric and assemble the parts together. Anybody could do that, because you guys been doing isometric since 4th form and 3rd form. But the issue that students have is really when it comes to section 2, where they lose 30 marks because they don't know these questions, right? So I want to spend majority of the time tackling these questions, giving you the confidence to really attempt these questions. All right, so everybody good with external threading? You just simply draw the beam as normal, but then put a 45-degree line and create a parallel line to the beam itself. Does that make sense?
Yes, sir.
All right, good. Now we're going to move on to our next topic now, and this is why I really want to do past paper questions, because it enables us to go to different topics easily while still doing questions. Sectional views. That's the next topic. All right? What is a section? If you're telling me that you're in a section at a party, for example, what does that mean?
A section at a party?
Yeah, like just give me the definition of what is a section really.
Specific area.
Right. Perfect. A specific place, somewhere exactly, right? You can pinpoint where you are. So when you're talking about orthographic shapes, what do you normally use to identify details that you can't see in front of you? What type of lines do you normally use? Exactly. So what sectional view is really is telling me exactly what is there by just looking directly at it. That makes sense. Let's go there. So a sectional view is just an orthographic detail that shows the inside more clearly than just using hidden detail lines. Right? So you're not just going to tell me, oh, there's something there. What if you want to draw or make that component? Just using hidden details wouldn't tell me what is there. So we use sectional views now to just look at that part of the object that has hidden details and explicitly draw what is there. Does that make sense? Let me give you an example. Look at this wonderful GIF I found. All right? So essentially, it tells you what is exactly happening here. Because if you were drawing this shape, you would have drawn just drawn some hidden lines, right? Just hidden lines going down, but it wouldn't have told you that was a shaft. So when you use a section line, you use something called hatching. Let me write that. So the little cross section that you see that's orange, I think. Do you see that cross section lines that is going at an angle? Let me look closer. There you go. Do you see those lines? Right here. Hello, do you guys see those angled lines going across?
Yes,
all right. We call those hatching lines. Let's go here. Hatching lines. So, Delano, a while ago you told me that it really hidden detail lines were used when you're looking at an object that you can't see, right? So essentially, what hatching lines does, it tells you the area that is hidden. So let's look at this, for example. When you cut directly between the surface to tell me what is there, whatever surface that is cut, you hatch it. You use angled line. Yeah, you angled. Right. So when, for example, I use an imaginary 1,000-degree hot knife. You know those compilations on YouTube where you just cut a shape, right? This is what you're doing with this design, where you just cut inside of it, and then you look at it exactly and tell me what is there. And if something is there that I didn't see, you use hatching lines. All right, so we're going to do more examples after this, but this is the real example of it, okay? Let's go to the question now. So we understand really what is hatching lines. Let's go to the question. So the question says, using sectional views that we just learned, explain how internal threading, which is the knot that we talked about earlier, Corey, how would you explain those types of knots using sectional lines? Let's go here, internal threading. Right, let's go here, good. So here is the entire drawing itself, and then we go inside to say, well, we have an internal groove inside of the knot, right? So here's what we would do. We would draw the knot just as exact. Then we would imaginarily use a 1,000-degree knife, cut half of it, and hatch anywhere that was cut. Say, for example, here, we hatch here, and then now the inside diameter of the knot itself, we leave empty. So here's what we do. We use thick, continuous lines to display what the drawing was, which was a knot. Then now when we cut inside of it, let's go back to the diagram of the knot, just to make sure you understand. Let's go here. All right, let's go here. So when I cut inside of this knot, right, there's going to be some areas that directly gets affected by that bisection. That's going to be the hatching lines, like right here. But you see, for example, wherever there is going to be the screw grooves, like wherever you're going to screw inside of, guys, you wouldn't hatch there. Understand?
Yes, sir.
Right. So wherever the screw is gonna go inside of, don't hatch that area because we already know that that's gonna be a diameter. But for the area that's gonna be cut to help you see exactly what is happening, you hatch that area. That makes sense. All right. So that's really the encompassing of what really the 30 marks would require you to do. But there's one more aspect: holes. So because the question didn't just say do internal threading, right? It asks you to create something called countersunk and counterbored holes. And we're gonna go through those. Don't worry. So now, what is countersunk? Right? Let's look at the two of these diagrams. Right? So if I had a screw and I cut it across, which section would I hatch?
The one that has been cut. Oh no, that's the flat. Right there, the arrows.
Right here, right?
Yes, sir.
Excellent, excellent. I wouldn't hatch right here, correct?
No, that's a part of it.
Exactly. Same thing for here. I would just hatch this section and this section, right? I wouldn't hatch inside of here because that's going to be a different type of screw called counterbore, which we'll be defining right now. So let's define what counterbore and countersink means. Countersink, you can just picture like a normal sink in your house. When you throw things down the drain, it essentially goes through a little bowl type of design. That's what countersink hole really means. A conical hole cut into an object, such as a sink, right? And the real directive towards having these types of holes, right? It applies to objects such as sinks or when you're making specified manufactured objects, right? It gives it a 45 angle inclination that could be really useful in some cases. Understand?
Yes, sir.
So there's specific types of screws that look like this that could fit inside of this hole, right? And I'll give you some examples at another time. But let's look at the counterbored hole now. So this hole was at a 45 degree, right? But the counterbored now is not. It's a cylindrical, flat-bottomed, right? Here's a flat bottom right here, that enlarges another hole, right? So in other words, this was the original hole. Understand? But because now we use a counterbored hole, we get a larger diameter that is above here. Understand?
Yes, sir.
Let me repeat one more time.
Sir.
Yeah.
Also, I have a question.
Uh-huh.
Will you post the link for this before class ends?
Yeah. So I'll post. Matter of fact, let me post the link now. So this is gonna be a virtual notebook. If you want, if you have a physical one, just take some little jottings from this, or you can just watch the video. Right? Let's go here. There you go. So that's the virtual notebook. You can just watch the video.
Thank you, sir.
You're welcome. I'm just taking attendance. There we go. Excellent. Let's go back here. So now, counterbored essentially is where you have original smaller hole, but now you enlarged it using a device or a tool to create a larger hole above. Understand? So that's a counterbored hole. The symbol is simply just a flat bottom design like that. And for the counterboard and the countersink hole, simply like a sink symbol. That everything goes to one point. So now your task, and again, I know you guys love doing your homework, so that's why I made sure to do this. Your task is gonna be to represent the definitions I just explained to you in orthographic sectional sketches. Let's go back what orthographic means. It's simply you're gonna tell me what is exactly shown when you're sketching these, like we did earlier to this drawing. Let's go back up here. Let's go back to the diamond knurling. So remember, when we did the knurling, we got this sketch, right? You're going to look at this counterboard and countersink, look at it objectively, tell me what section is going to be hatched, right? And how will the convention be? How would it generally look? So for example, let me give you a quick little hint because I encrypted this file, but let me just, because when you guys are on it, you won't know what the password is, but I'll just de-encrypt it and show you an example. All right, my bad. Let's go here.
Sir, can you send the homework in the WhatsApp chat, please?
Yeah, not a problem.
Like the detail.
Yeah, not a problem. So I'm just gonna copy one of the pictures. Here we go, and I'm just gonna show you one example. There you go. Technology is awesome. There we go. Right? So this is an example of the counterboard hole. Do you see where the flat bottom part is right here? Let's go back to the picture. Here's the flat bottomed part. So you would draw essentially the flat bottom part right here, and then show me what the inside diameter would have been, and then now hatch some parts or the part here that would have been cut. Understand? Everybody understand? So you can either use an endless screw like this, or you can just design a screw for yourself where you just show me the flat bottom part and then extend it to a certain distance and then tip it off to show it's a screw. Sounds good?
Yes, sir.
All right. And then now for the last one, I won't show you a visual example. You are going to try to interpret it based on the counterboard one I just gave you a while ago. Tell me, how will this one look in an orthographic sketch? All right. So that's really the agenda. And hooray, we just got 30 marks on an exam and we took less than 30 minutes. So good. But practice your sketching. So I want to see how well you guys are at freehand sketching. So just do these two activities, right? And then I'll quickly grade it for you. And I'll tell you where you can improve on and so forth. But now what I want to get into, right? That was just question one. I thought it would have taken me up to the 45 minutes. But since it didn't, that's good. So what we're going to go into is the SBA. All right. I spoke to some of your parents earlier this morning. And I just informed them that they got the SBA to start. And I just want to know exactly where you guys are. So, any updates? Any difficulties you guys are having?
Not really difficulties, but I guess we're all kind of lazy. So we're gonna work on it.
Can you repeat?
We're all just procrastinating.
Yeah, like it's not hard. We're just
not a problem. So here's what I'm gonna do. All right, because the whole reason for this textbook is really to make procrastinating less. All right, I'm gonna create right here, Corey. So I have it in my register already. I'm gonna tell you who I don't have here, and the reason why I'm gonna put your names here, I'll explain 1 second. Jessica, I have you there. Josh, let me show you everybody that I have some work for. Patrick, yeah, I have work for you.
Report cards are coming out, so I want to get people to work on this.
Right, so that's what I'm saying. So what I want you to do, spend the rest of the time finishing up on the parabola, so I can just put that as your coursework, and I can have a grade for you. Because for some persons I don't have any grade, or even for the SBA, just go and finish it up. Sounds good?
Yes, sir.
All right, so this.
Did I do the parabola? Can you let me know?
I can check quickly for you. Let me just check. I don't think you did though, because I would have got a notification. But tell you what, the portal is still having a little bit of issue. So please just send me the email with your work, just in case I don't get a notification for the portal. All right, because I can mark it outside and just upload the grade. Not a problem. So for example, for Corey's case and Delano, you guys wouldn't have to send me an email, because remember I shared the same server with you. But just tell me when you finish a drawing so I can just go and check it. Okay?
And sir, you said for the parabola that it's on YouTube.
Right, I spent the whole weekend, guys, designing. So let me show you exactly the YouTube page and where exactly you guys gonna go. Send me this. Yeah?
My parabola, right?
Uh-huh. Wait, I can't hear you. Can you hear me?
Sir, you're cutting out.
Oh, I'm cutting off. Let me